Hi guys, I am going to show you this kind of virtual lab game thing about enzymes in case you're struggling with it on your computer. So if you guys take a look, it's called Enzymatic. I'm going to click start a new game. I don't have an iPad, so I'm going to do this on my computer and say no touch screen. And I'm going to start by taking a look at this background. It says enzymes are very important in biology. Every life process relies on enzymes basically inside of every living organism. So it's probably important that we understand enzymes, which is why we're talking about them. This is a little kind of interactive virtual experience thing where you get to see some properties of enzymes. So we're going to start here. And the one that I asked you guys to do is this purple button that says experiments. So we're going to click experiments. It says enzymes are affected by factors like temperature, pH, which if you remember the pH scale was acids and bases, and substrate concentration. Substrate, remember, is the molecule that fits in with the enzyme. So how much of that substrate is available also is going to affect the rate of an enzyme catalyzed reaction. So several factors will affect how well an enzyme is able to perform its job. For example, enzymes are affected by temperature, pH, and the concentration of those substrates. All of these factors will affect the rate at which this chemical reaction is going to be catalyzed. And remember, a catalyst means something that speeds up reactions without being consumed by it. That's what an enzyme is. So we're going to determine how those factors affect enzymes by doing a couple of virtual experiments. So we are first going to look at temperature. We're going to enter the lab by pressing OK. So it says very slowly drag the slider to see how the reaction rate of the enzyme is affected by changes in temperature. We're going to make some observations here. So look at the slider. Right now we're at like no temperature gauge here. We're just at a start. And we're going to slowly move this temperature gauge up. And as I get warmer, you can see everything starting to move faster. Look at my graph here. Slowly from a cold temperature to a warmer temperature, it's starting to go faster. And you can see that with the molecules. You can see that here on this graph. Look at that. We're going faster and faster and faster. And now we're kind of near the top of our hill. And as I continue to get warmer, you can see it's actually starting to go down a little bit in terms of speed. Something's off. Let's keep going warmer and warmer. Look at this little text box. It says our enzyme is starting to denature. And remember, denature means something's going to change the shape of my enzyme. Look at that. The shape's starting to get wonky. Uh-oh. The higher the temperature, the more it's getting wonky. It's getting uglier. It's getting all deformed. Ugh. Not good, not good. Let's go up to a very high temperature. Uh-oh. Look at my enzyme. That is not the shape that I started with. And that is not the shape that's going to fit with that substrate. Look, there's no way that's going to fit in there. And now the enzyme doesn't work anymore. You can see in the graph right here, guys, that the rate of reaction is all the way back down to 0 because it's not working. So let's go back. Let's see if we can just turn the temperature back down. Uh-oh. Even if I put it back to normal, doesn't work anymore. It's too late. We ruined our enzyme. We denatured it. And now it's no longer going to function. So we could start over with a fresh enzyme and look, we can repeat the same procedure. It's going to go faster and faster till we get to that like ideal temperature. And that's going to be the best rate. But once we go too high and we denature it, uh-oh, not going to work anymore. Okay? It is denatured. It's deformed. It no longer functions. Okay? So think about this. The temperature at which the enzyme works best is called the optimal temperature. The optimal temperature is the temperature where the rate is the fastest. And you can see that right here on this graph. At about a 37 degrees Celsius, that's where this reaction was going the fastest, ideally optimal temperature. So let's use that to think of the answer to this question. It says based off our observations, which would be true? Substrates, those little molecules, move faster at higher temperatures. Well, that was true. We saw those little squares move faster the warmer it was. 2 says faster moving substrates collide with the enzyme more, causing the reaction rate to increase until you get to that optimal temperature. Also true. It went faster till we got to that ideal temperature. And then thirdly, hotter temperatures always result in faster reaction rates. Well, think about that. Even when we went all the way to the end of the slider, that was too hot. Now my enzyme didn't work as well anymore because it was denatured. In fact, it got to the point where it didn't work at all. So the correct answer would be 1 and 2 only. Woo! We're right. Let's go on to next. What is the optimal temperature for the enzyme shown below? So let's look at the optimal temperature here. If we see this graph from 10 to 60, let's look at where the reaction rate is the fastest, okay? Where it is the fastest without going back down. So right around 40 degrees Celsius, that's where you can see it went up to the highest peak on our little hill, which means the highest rate of our reaction for this enzyme specifically. A. Woo! 2 out of 2, baby, 100%. It says, why does the reaction rate slow down drastically when the temperature is too high? Why did it really get messed up when we turned up the temperature too high? A, the substrates were just too fast. B, the enzyme loses its shape, aka gets denatured, and it can no longer catalyze the reaction, make it go faster. C, it loses color and attractiveness. Or D, the enzyme and substrate are stuck and can't separate. Well, what happened when we turned up the temperature so high? What happened to that enzyme? Do you remember how it got all weirdly shaped and it didn't fit the substrate anymore? So the answer for this one, think about it, B. It no longer has the correct shape because it was denatured. All right, I think this is the last one for this section. Based off your observations, which is true? A, the denaturation of the enzyme is necessary for it to work. No, we don't want it to be denatured. Get rid of that one. The denaturation of this enzyme by heat is reversible. In other words, when you lower the temperature, it fixed the shape. When I lower the temperature, did it fix itself? Did not work. C, the denaturation does not affect the enzyme's function. Or D, the denaturation is irreversible. You cannot fix the shape once you've gone too far. Well, that is true, because when I went up and I tried to go back down, it was still denatured and it still didn't work. D is correct. Amazing. All right, so next we're going to take a look at how pH affects enzymes. All right, guys, so for this section, we have to think back to the pH scale, which Mr. Richards taught you. When we use this scale, we're describing how acidic something is or how basic something is, acids and bases. Remember, something that's very acidic is going to be lower numbers on our scale, like 0, 1, 2, 3. Things like lemons and soda and I'm trying to think of something else that's really acidic. Citrusy fruits, even coffee is a little acidic. Okay, those things are going to be lower on my scale. Okay, hydrochloric acid is really acidic. 7-ish is like neutral. That's water, good water. Okay, and then over here on this scale, up closer to 14 is basic, like toilet bowl cleaner or bleach. Okay, very basic. So some of those things are going to have an effect on our enzymes. So that's pretty okay. So here's my enzyme working with the substrate. Cool, cool, cool. We're going to slowly drag this slider to see how the pH change affects my enzyme. So I'm going to make the pH go down. That means more acidic. So as I slide this down, guys, look at my graph. The rate of the reaction is going slower as I make the pH lower because it's changing from what is the ideal pH. If I go all the way down, starting to denature, Since our enzyme is denatured, it means it's lost its shape. It does not work at this pH at all. Sometimes an enzyme can regain its shape after being denatured if the pH goes back to its optimal range. So let's see if that's true for this particular enzyme. Let's go back to my ideal pH somewhere here in the middle. Oh, look, it still works. So sometimes it can be reversed when we're talking about pH. Okay, now speaking of pH, let's go the other direction. Let's go to a high basic number. Let's go to like 9, 10, it's going slower, 11, 12, 13, 14, zoinks. Look at that guy. Not gonna work anymore. It's denatured. Remember, if it's denatured, that means the shape changes. If the shape changes, it doesn't work. So once again, we've changed the pH away from our optimal pH, our favorite, best, fastest reaction pH. If we go back, look, we fixed it for this. Okay, cool. Whew. Temperature, we couldn't do that. But for this particular enzyme, the pH could return to its optimal value and fix it. So based off our observations, which would be true? Substrates move faster at higher pH levels. Did they move faster when we did that? 2, there's an optimal pH at which the enzyme works best. Above or below that optimal level, the enzyme becomes less effective. And that was true because I moved it up and down and you saw that it went slower as we went too high or too low. Thirdly, the enzyme denatures, or remember, loses its shape at the pH level that is too high or too low. So I'm thinking we should try to pick numbers 2 and 3, okay? Because I don't remember the substrates moving faster just because we turned up the pH. So let's pick B. Oh my gosh, we're right. Let's try the next one. What is the optimal pH for this enzyme shown below? So look at my graph. You can see where was it going the fastest, right here. So about 8. Let's pick 8 as our optimal pH. Perfect. That's optimal because it's where the reaction was happening the quickest. Thirdly, based on the observations we saw, which is true, the denaturation of the enzyme is necessary for it to work. Denaturation means it's not working anymore. B, the denaturation by pH is irreversible. If we went back to the optimal level, it didn't fix the shape. Well, that actually isn't true for pH because if you remember, I did go back to the optimal level and it was okay. So sometimes that's true for pH. Denaturation does not affect it. Or D, denaturation is reversible when we're talking about pH sometimes. We restored the pH and we fixed the shape. That is true. That's big D. Oh my gosh, we're amazing. Okay, pepsin is an enzyme that's in your stomach, right? I would never ask you to know the name of that enzyme, but I'm giving you an example of one. That's an enzyme in your stomach right now. It's very acidic in your environment, in your stomach environment. Which of the following would be the most reasonable inference, meaning if you were going to assume what would be the optimal pH for this enzyme? So wait, we just said that this enzyme lives in your stomach. The stomach is very acidic. So what kind of number are we looking for that's very acidic? Low or high? Well, remember, 7 is neutral, so that's not our stomach. High is basic. Low is acidic. So let's pick something like 2. Great. So you might say, well, that's really acidic. Didn't we just show in this observation that acidic environments are more good for enzymes? Some enzymes cannot exist at such an acidic environment, but some enzymes love acidic environments. It just depends on the enzyme. This one lives in your stomach, so it wants to be in an acidic place. Okay, how about, lastly, let's look at how substrate concentration is going to affect our enzyme rate of reaction. All right, so our last factor, substrate concentration. Remember, substrate is the molecule that fits perfectly with my enzyme, whatever shape that might be. So we're looking at how much substrate is going to affect the rate of the reaction. So if you think about a higher concentration, that means more substrate molecules. Higher concentration means much more substrate is available. Lower substrate concentration means less substrate, so less available molecules for the enzyme to act on. So let's make a hypothesis. What do we think is going to happen when we change the substrate concentration? So because I am a super genius, I think I can make a pretty good hypothesis here. Let's say a higher substrate concentration will result in a faster or slower rate of reaction. I'm going to go with result in a faster rate of reaction because I think the more substrate you have, the faster the whole thing will go. So we have our substrate concentration slider. We're going to slowly drag the slider to see how the rate of the reaction of the enzyme is affected. So right now we're low. We're at like so low I don't see anything. Let's slowly move it up and see what happens. You can see on my graph, as I increase the concentration, it's slowly going up in terms of the rate. So I'm going to keep going, keep going. Wow, it's still increasing. That's great. More substrate, baby. Hey, it's not really increasing anymore. It's not going down, but it's just kind of flat. So I'm all the way at the highest level. I can't add any more substrate. If you guys look at my graph here, you can see it goes faster, 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 faster. Then you kind of get to a certain point and it just levels off. So think of this like peanut butter and jelly sandwiches. If you have a bunch of pieces of bread with peanut butter on it and a bunch of pieces of bread with jelly on it, you can make a bunch of PB&Js. And if you keep adding more and more slices of bread with jelly, you can make more and more sandwiches. But at some point, you have so many slices of bread with jelly that you just don't have enough peanut butter slices. And that means that you've kind of hit your peak of PB&Js that you can make. So this is the same idea. At some point, you have so much substrate that it really doesn't matter if you add more. There's just not enough enzyme to make the reaction go faster and faster and faster. So based on our observation, how does the substrate concentration affect the enzyme activity? There's more enzyme activity at higher substrate concentrations due to more collisions between the enzyme and the substrate until you reach a maximum rate of reaction. Well, that is true because at some point we just hit our peak. 2, the maximum rate, once we reach that maximum rate, the reaction levels off. And you remember, you saw that in the graph, it kind of got flat. 3, the reaction rate will always increase as substrate concentration is increased. Well, that's not true because we got to our third point here and it just leveled off. And even though we added more substrate, it didn't go any faster. And that's because we've reached our maximum amount of bread and jelly sides that we just don't have enough bread and peanut butter sides to make our PB&Js. So let's pick 1 and 2 as our option. Okay, moving on. How is enzyme activity at varying substrate concentrations different than when we change the temperature or pH? A, 1, the graph for substrate concentration shows the rate leveling off when the substrate concentration is high instead of declining when we're not at the optimal range. That's true. Remember, we didn't go back down when I added more substrate. We just leveled off. 2, when increasing substrate concentration, it's apparent that the enzyme denatures, but that's not seen when you increase temperature or pH. Did we denature our enzyme in this one? Because I don't remember doing that. I have pretty good memory. All right, 3, changes in substrate concentration do not cause the enzyme to denature, but pH and temperature do cause it to denature. Now that sounds like a good one. Let's pick 1 and 3 and see what happens. Oh my gosh, we're good. Okay. What about this? Was your hypothesis supported by our activity? Well, yes, I correctly predicted. Now, if you made your own hypothesis and you were wrong, great. That's awesome. In science, it's great to be wrong because we're still learning something. Every time you reject a hypothesis, you're still learning. So that's still wonderful. Let's say yes because whatever. Ooh, now we're at our last piece of the puzzle. Let's make this enzymatic machine work based on what we've learned in the previous sections. All right, guys, so we're now at the enzymatic machine. We need to make this sucker work by applying the knowledge that we've just learned in our activity. So it says first, choose the appropriate enzyme for the substrate. Remember, an enzyme and a substrate need to fit together perfectly, like a lock and a key, like a hand and a glove. They need to go together perfectly. And if we look at my 3 options here, this is kind of a square active site. We don't want it. This has a pizza slice active site. We don't want it. Let's pick the orange one because that clearly fits with my little round substrate. Super, we are correct. The active site, remember the area where they fit together, matches perfectly with that substrate. Now it says, let's select the optimal temperature for this reactor using our graph. So here's the graph that we're given. You see that we want to go to where the reaction rate is the fastest, right here. And you can see that the ideal temperature is somewhere around 30. So let's put 30 in there and set our temperature and see what happens. Woo, we are correct. We picked a good temperature. That means it's going to go the fastest in terms of the rate of reaction because we've selected the optimal temperature. Now let's select the optimal pH. Look at this graph. If you were looking at, once again, the rate of reaction, we're looking for where it's going the fastest. So you could say that says 6 and that says 8. You could go with 7, 7.5. Bet either one would work. Let's put 7 in there. pH. Oh, we are correct. We found the optimal pH. That means that enzyme is going to work at its fastest rate without being denatured. Ooh, last piece of our puzzle, substrate concentration. Remember, if we keep adding substrate, we could do like 100%. And that would just be too much because it wouldn't go any faster, but we added a lot of substrate. So it says, let's put a reasonable substrate concentration where it's going to go fast, but we don't want to put too much substrate because we'll clog our machine. Okay, and we're just making that up, but whatever. So if we're low, like at 4%, that's not fast enough. If we're at 12, that's too high because it's not any faster than if we were over here at like 8, 7, something like that. Let's try 7 and see what happens. A little too low. Where's 7 right there? Okay, not quite optimal enough. So let's go a little higher. Let's go with 8. Let's put 8% substrate concentration. Super. Okay, we're not too high that we're like just leveling off, but we're high enough that we're at that optimal level. Okay, so now we're going to watch our enzyme work. You can see the substrate going in, and this particular enzyme is splitting the substrate. Sometimes enzymes build things, sometimes they split them apart. Just depends on the enzyme. So once again, we're watching this happen. Ooh, my enzyme is splitting up my substrate. Look at my products. The substrate goes in, that's my reactant. The product comes out. Beautiful. Look at all that work being done at an optimal rate. So we correctly applied our knowledge. We made the machine work. We are amazing. So using what we saw in this video, what you guys saw in this activity, you can answer those questions on your own, and you can think, how does temperature, pH, substrate concentration, how does that affect enzyme activity? Remember, we have an optimal temperature, the best temperature. Too high or too low is going to reduce my rate of reaction, maybe even denature my enzyme. pH, we have an optimal pH. Too high or too low is going to possibly denature my enzyme and reduce the rate of reaction. We have an ideal substrate concentration. And once you get to that optimal level, adding more is not going to denature my enzyme, but it's also just going to stay stagnant. Super. Awesome job, you darling angels.